Hi, I'm Soumyendu from Hewlett Packard Enterprise, and our paper is on carbon footprint reduction for sustainable data centers in real time. What is the motivation? On the bottom left, we can see how the data center is supplied from a power grid whose carbon intensity, that is, the availability of clean energy, changes over time. Also, the workload and the weather have effects on the energy consumption. Now, our objective is to lower the carbon footprint, the energy consumption, and the energy cost. To do this, we need to think beyond optimizing cooling energy to flexible load shifting and energy storage. Going into more details, this requires optimizing the power consumed in cooling and IT load together for the data center and shifting flexible load based on the availability of renewable energy in the power grid and leveraging the battery storage from the UPS in the data centers. A real-time controller that optimizes the data center for these goals is lacking. Now, on the bottom right, we can see how the physical system maps into a digital simulation. Even though our framework supports multiple model options for evaluation for benchmarking, we have used industry standard components with Energy Plus from NREL for the data center thermal model, the Stanford Facebook battery model, which captures the nonlinear response of the battery for charging and discharging. We have an OpenAI Gym wrapper, that is the abstraction needed for using machine learning or reinforcement learning controllers. Now, even though for this paper we are focusing on the digital data center simulation, this can be part of a digital twin with control interfaces and IoT sensing, which we are currently building. Now, the complex interdependency between the three agents and the information exchange required across these separate controllers have resulted in researchers tackling these problems in isolation or in static analysis form. Also, the static analytic approaches rely on long forecast horizons, like for a day, and generate a day ahead schedules, which are very inaccurate because of variations of weather and grid carbon intensity and the data center loads variations. Now, the multi-agent reinforcement learning is well suited for problems like this with multiple controllers. It can simultaneously optimize the data center cooling energy, the load shifting, and the battery operation decisions, thereby reducing the carbon footprint in real time across all three avenues. Now, our approach relies only on instantaneous data and short-term forecasts, making it a much more optimal solution for decisions. Now, we developed a simulation framework called DCRL Green. It is an OpenAI Gym-based design for developing and evaluating a collaborative heterogeneous multi-agent reinforcement learning controller for these data center optimizations with a focus on sustainability. Now, it supports a number of different modules like cooling, load shifting, battery, and these are all pluggable modules. For instance, the cooling module can use Energy Plus, or you can plug in HP's Pythonic configurable data center, or you can bring in your own data center model, say, which you have developed in Open Modelica. Now, we'll publish more details in an upcoming publication for this framework. Uh, the Our custom data center model also is part of this environment. And our framework supports an extensive data center configuration with our highly customizable Pythonic data center models where you can specify the individual servers within racks. And the customization covers the data center geometry, the server characteristics, and the HVAC specifics, and external influences like workload profiles, weather, grid carbon intensity, etc. This customizable HP data center model was published in ACM BuildSys. Here we used the Markov decision process to define the problem. MDP is a mathematical formulation for reinforcement learning that provides a formal way to model decision making in a dynamic environment where the agents take actions based on the state of the environment and the results of the actions determine the rewards and subsequent states. Now, the reinforcement learning is effective in diminishing data center carbon footprints by synchronously solving these three MDPs and systematically accounts for agent interdependencies. And also, the rewards are shaped, as you can see on the bottom right, for a collaborative multi-agent reinforcement learning. Now, here you can see our sustainability dashboard for data center. On the top, you can see the different results where green is us and red is the industry standard AAAI rule-based controller. And there you can see the energy consumption, the carbon emissions, and the energy cost. And we are low, that is the green, we are low on than the red, which is AAAI. Now, in the middle row, you see the different contexts, which is like the carbon intensity in the power grid, the workload variations, and also the DC room temperature, which kind of like follows some of the external temperatures with the cooling. Now, on the bottom, you can see the actions, which is the shifted workload and also the HVAC cooling set point and how the battery is charging and discharging. Now, we explored different multi-agent reinforcement learning methods, notably the multi-agent deep deterministic policy gradient, that is the MADDPG, which employs decentralized agents learning from a centralized critic. And we also explored the independent proximal policy algorithms, and that is the IPPO, which is tailored for collaborative yet independent agent actions. And now both converged to similar performance outcomes. Now here we are showing how the different locations like Arizona, New York, and Washington state varies in terms of temperature and humidity on the bottom, which affects the data center cooling efficiencies. Now the graphs on the top shows the carbon emissions of different locations across seasons for a data center model, which is 1.2 megawatt hour size. The orange is AAAI, that is industry standard, and the green is our solution, and lower the better. Now here Arizona has a high temperature, low humidity, and high grid carbon intensity, while Washington is opposite and has low temperatures, high humidity, and low grid carbon intensity with a lot of green energy in the grid. And as you can see, our solution outperforms AAAI across the board. In this table, we look at the savings attained by incrementally applying the three different carbon footprint reduction strategies when compared to the baseline strategy of using AAAI rule-based controller. And our framework reduces carbon emissions by 14 to 15% compared to the baseline. And compared to the baseline for the HVAC controller for the data centers. Here we used the data center modeling with a max load of 1.2 megawatt hour and using the Energy Plus and IPPO for multi-agent reinforcement learning. Now, this shows a similar effectiveness in reducing both the energy consumption and the energy cost. Now, the HVAC cooling, it can be seen that our approach shown in the green spends more energy in cooling than the industry standard AAAI shown in orange on the top left. But there is significant saving on IT energy as shown on the bottom left, which leads to a lowering of the total energy shown on the top right. Here we show how the load shift is working. The grid carbon intensity is in gray, the baseline load is shown in red, and the shifted load is shown in green. As we can see, there is significant shift in load from times when the carbon intensity is high to times when the carbon intensity is low. Now, this shows the energy storage of the battery controller. The energy storage agent implements energy hedging mechanism for storing energy when the cost is low or the carbon intensity in the energy grid is low and spending the energy at periods of high cost. This shows how the battery charges and discharges. This figure shows the variation of carbon footprint across a whole year for New York and Arizona. Now, in conclusion, here we're using the method which can reduce the data center carbon footprint, the energy consumption, and the energy cost with a holistic approach which includes load shifting and battery storage in addition to the HVAC cooling optimizations. We introduced a cooperative multi-agent reinforcement learning for joint optimization in real time. Also, the resultant carbon-aware load shifting factors in weather and with carbon intensity. This modular approach is scalable and flexible with the plug-in options, and the modules itself are extendable. Thank you.